Hello everyone, I'm Jaehyung and today I will talk you through audit-driven signature tracing for smart contract security. And I work mainly on blockchain security, things like smart contract auditing, vulnerability analysis, and automated reasoning about on-chain systems. Before that, my background was in programming language theory and static analysis, like some automated program repairs or something. That mix of practical audits and formal methods is what got me interested in today's topic. So before diving into our proposals, let's briefly review what blockchain and what makes smart contracts different from normal softwares in industry. Think of blockchain as a public append-only spreadsheet replicated worldwide. Each block includes a timestamp and transactions. By the way, most of you guys are familiar with blockchains. Then I will just skip it. And everyone familiar with it? No? Okay, no answer. So then I just explain it. Yeah, each block includes a timestamp, transactions, and a cryptographic link to the previous block. And that link actually means the prior block's hash makes the chain temporarily evident. If you alter the past block, all the hashes break and the network rejects it. Because every node owns the same ledgers and verifies the same history, is considered as a trust minimized system. Modern blockchains extended this idea just by not allowing only the data, but executable code to reside on-chain. So the resided codes are called smart contracts. The smart contract is actually a small program that runs directly on the blockchain. When a user sends a transaction to this contract, it triggers one of these functions, and the blockchain records the result permanently. And so this aspect has two important consequences of that. First, every operation costs a small transaction fee because validators need to execute the code and verify its results. They spend a computational cost, so it's for the compensate. Second, is important. Once a contract is deployed and executed, its results are almost impossible to reverse. We can reverse it, but it needs a huge community consensus. So if there is a mistake in the logic, for example, a bug that moves some tokens incorrectly, it can directly lead to the real asset loss. So because the contract itself usually holds the transposed value. Smart contracts are implemented across the major blockchain systems, platforms each with its own execution environment. For example, Ethereum side, like with clients like Hyperledger Besu, contract run on Ethereum virtual machine, or called simply EVM. And they are typically written in languages such as Solidity and Viper, and more recently, experimental ones like Health and Faye. On the other side, Hyperledger Fabric runs code inside an isolated sandbox. It's actually a Docker, supporting languages like Go, Java, and TypeScript, and also even bytecode and Solidity for compatibility. And in the normal softwares, a bug might crash of an app. But when it comes to the smart contract, bug might move funds to the wrong place or let an attacker drain some funds. Attacks targets value, not just it means that attacks target value, not just availability. We broadly group issues in two main categories: flawed design and incorrect implementations. Design flaws lives at the business logic level, and on the contrast, implementation bugs lives at the code level. Design flaws usually come from incorrect requirements or wrong assumptions rather than coding bug itself. For example, in the slides, you can see some illustration. Take the case of the price oracle in the Lightning protocol. If the oracle somewhat failed to take some prices and accidentally reports some prices that are too high, and the protocol developer misses this case, the protocol might believe the collateral is worth more than really it is, and it will end up insolvent. These issues are tricky to detect with normal pattern matching or static analyzer tools because its problem is not just in a single OP code or statements. It's in a false assumption about how external data or contract behaves. Most of these weaknesses stem from the missed edge case or security assumptions that actually doesn't hold. And on the other side, incorrect implementation, it's just bugs, are even earlier to recognize and pattern match. They include things like, but there are some notionable examples like incorrect access controls or improper user input validations, integer overflow and underflow, just available, causable in any normal softwares, and the classic errors like rand trust issues is actually just specified for the smart contract where external calls can re-enter the contract before it finishes updating the critical states. These type of problems are generally more amenable to automated program analysis because they appear as recurring code-level patterns that can scan for or detected by static or dynamic analysis. So how do developers or projects reduce such risk recently? There are some methods. For example, they run audit contests or some audit services, or just run smart contract analyzers, open source, and they just simply give them code and spec documentation to LLM and ask for assessing security. And actually, all three methods seems useful. And I will explain each method and its own challenges as well in detail. For first approaches are conducting audit contests and services. Yeah, audit services are pretty familiar. Just request an audit service to companies, and they allocate professional auditors for some scoped files and times. And when it comes to audit contest, audit contest is mobilized dozens of independent auditors and all around the world for a fixed time with some real pool. You can see that in the slide. There are some projects called Kinetic. They request 9 days of audit times, and they deposited around $35,000 for the reward. And the reward will be given to auditors based on their findings. It's related. The amount of reward is related to severity and rarity. And when the audit ended, audit reports are delivered to the projects, and reports are usually include severity of vulnerabilities and detailed description and related code snippets, proof of concepts that the test code can be reproduce the bugs and a patch. Surprisingly, it's often published by the audit firm itself or the project as a proof of audit. They want to prove the their software is secure, but with some documents. And since the report covers rich and detailed data on vulnerabilities, so it's actually the gold mine of security knowledge about smart contracts. So many students start with studying about smart contract security with reading audit reports. But there are some challenges to learn from these gold mines. And there are no standardized formats. So audit companies and audit contests publish their own standards, so the knowledge cannot be organized consistently. And audits are often treated as a pre-release activities, so they are not tied to the post-release threat management like CVEs or sneaks. And there are no unified database to capture and these use lessons. So you need to find audit reports one by one to company by companies to learn lessons from smart contracts audit service reports. And open source analyzers are also appealing approach for the smart contract security, because smart contracts are often manage large amount of valuable assets. So both academia and industry have been actively developing and improving smart analysis tools. And broadly speaking, there are two main approaches in automated program analysis. Static analyzers, which examine the source code or bytecode without executing it, and dynamic analyzers, which inspect runtime behavior or simulations. More recently, researchers have been exploring the use of large language models to analyze analysis performance and reasoning capabilities. And there are a wide range of tools. The automated analysis tool exists, for example, the SAM-graph is not just for the smart contract, but for the various languages, for rule-based scanning, and to the MISEX and Adrin to the Slider, and well, it's actually specialized for the Solidity and EVM-based contracts, since the EVM-based and Solidity is the most general types of smart languages and environment for the smart contracts. But even with the automated analysis, still there are significant challenges. As we mentioned earlier, only a limited number of vulnerabilities can be expressed as the clear patterns, which means the number of effective detection rules is relatively small compared to the flawed designs. In most cases, these tools are required, another challenge is they need code. In most cases, these tools require access to the full source code. They need to build or pseudo executing, which isn't always available for the on-chain contracts. And finally, analysis is usually costly. So analysis at scale is also very costly, both in computation and time, making large-scale on-chain scanning difficult to perform efficiently. When it's different for the LLM-based approaches, we expect LLM-based approaches hold promise because it can spot issues that fit neat rule-based patterns. However, LLM-based analyzer has also practical limitations. First, LLM often struggle to explain why a finding is a truly vulnerability. They give answers, but not a rigorous proof. And second, their outputs can be inconsistent from run to run and hard to pin down with some guarantees. No formal proof, no validation, even they don't give a test case. So in the slide, there are some conversation with some domains, smart contract auditing specific LLM service. I asked them to give some proof for the LLM-based findings, but they refused around 20 times, so I just gave up. And LLM also improve when they can draw on rich external knowledge. Our reports are often fragmented and inconsistently formatted and even hard to reach. So the model's background information is usually incomplete. So in such circumstances, such circumstances reduce the reliability and makes it harder to trust LLM-based findings. So to address such many limitations, we propose a signature tracing method that works in hand with both large language one-day analysis and LLM-based reasoning. Idea is pretty just simple. We extract concrete evidence from audit reports and convert it to reusable bytecode-level signatures. These signatures are stored in small open JSON format that anyone in the community can propose or review and share them easily. And there are no just easily patterns like converted into bytecode signatures. We want to give them at least give some LLM analyzers to some knowledge base. So for the more complex non-pattern cases, we complement those signatures with LLM or expert-generated summaries and verifiable witnesses, which means just a small test or formal proofs that show why finding matters. Finally, we plan to publish these signatures in some SPDX or VEX compilated formats so they can integrate directly into existing CI pipelines or alerting systems and security policies. So there are several ways to turn audit reports into the reusable signatures. I hope to share I want to present you guys with exact numbers with the actual effectiveness, but the numbers aren't finalized till presentation. So I just walk through the method conceptually. The approaches we want to implement includes some opcode sequences or regular expressions over the compiled bytecode, and function and event signatures, which means that just 4 byte selectors and event topics, and diffs between the original and patched code, and executed bytecode traces captured from some exploits or POCs. For every signature we generate, we also store links or some references back to the original report and patches so anyone can reproduce how the signature was derived. That provenance, that is what makes the whole process auditable. Yeah, let's start with I'm going to explain some approaches to translate reports, some signatures. Let's start with the simplest case, when the patch exists. In that case, we build a signature directly from difference with the buggy version and patched version. The idea is also straightforward. Just we ignore small variable level differences, like a specific storage stores and function names. So the signature works across compiled versions. Second, when new code is added, we look at what comes right before and after it in the control flow. And third, once the patch is present, forks and clones are already included in our automatically marked as not affected. That helps cut down the false positives. And it's under slides, the simple illustrations. There's a buggy code, this means an external call happens before the state updates. And the patched versions is a reverse it, the update burst, and then the external call. It usually shows in the re-entrancy issues. And we detect this change in our order of the 2 byte sequences, and represented is a signature. For example, using a regular expression or just similar matching patterns. And sometimes an audit report includes proof of concepts or step-by-step attack transactions. In those cases, we simply run POC once in our local nodes, either locally on the proprietary fork, and record the execution trace. From the trace, we extract a short sequence of executed bytecode that represented risky paths, essentially the part of the code that actually caused the issue. For example, in the trace shown here, we can see that the balance is read but not decreased before the external call token transfer, and that the one function appears afterward. The summarized paths look like the S-load, the balance load, and transfer calls, and blah, 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 as I mentioned in natural language. We turn that into a signature, something like risky execution paths observed at the runtime. And if a signature becomes more stable when it comes to with the patch exist, we replay the same POC on the patched build. And if the vulnerable subsequences disappears or changes, that gives us confidence in a patch and helps refine the signature to the reduced false positives. We just using some simple set theories. And not every vulnerabilities with clean, repeatable patterns, as I formerly mentioned. For these design or logic level issues, we generated 2 complementary pieces of information as shown on the slide. First is a short fact card. It lists key entities, underlying assumptions and preconditions. It's essential because to abstract the local design or logic level issues, because usually design load-level issues are hardly coupled with its application specifications. So we first design some entities and some abstracting by defining entities and assumptions. And second, the witness is a small verifiable artifacts such as boundary tests or lightweight SMT queries, simply used in static analyzers. Together, the fact card and the witness form a bridge between human reasoning and automated validation. And the fact card explains the issues in plain language, and the witness provides machine checkable proof that the problem really exists. And these knowledges might help LLM-based approaches to build concrete machine automated validation for the proof for their own findings. And example is this slide shows an example. Consider a price oracle that updates instantly from a single source. An attacker can use a flash learn to temporarily push the reported prices to an extreme value and then manipulate a lending protocol that relies on the price, all inside one transaction. Because the exploit depends on economic states, timing and interactions across the multiple contracts, as simple static rules usually miss it. For these cases, we produce a fact card that records the relevant entities, for example, entities lending pools and price oracle and collateral tokens. And the key assumptions, there is just some security assumptions like no TAAP. It means Oracle gives the time-weighted average price. They can respond to some imminent large price effect. We then supplement the fact card with runtime traces or simulated witnesses to confirm the issue. The combined package, fact card plus witnesses, is attached to the signature so anyone can understand the assumptions and reproduce the findings. And this slide shows a very simple example of the JSON schema we use for our signatures. The first few halts are straightforward. There's an ID, then which chain ecosystem you use, and short summary describing what signature defects. The pattern halts field is flexible. It can include some OP code regular expression, a list of function selectors, or even a small graph fragment. There's some fields for the designs. We can also specify what must be present or must not be present using optional anchors. And the contract side field has localized binding. It can point to the selector hint, a range of prime counters, or a hash of relevant bytecode slice. Finally, the witness and provenance field are strongly recommended. They link back to the test or proof that validates the issues and to the original audit report or patch that the signature came from. Keeping this small and consistent field make the format easy to share and review and reproduce. And this slide shows the workflow we follow to turn audit reports into reusable signatures. It's a simple six-step process. First, we collect all the relevant materials of the report itself, any linked code to snippets and sections and patches. Second, we generate initial signature candidates. These might come from OP sequences or some function selectors or code diffs on something. And third, when the issue is logic level, we also create a small fact card and witness template to describe and verify it. First, we try to reproduce the finding locally and run witnesses to make sure whether it's valid. And we finalize signature in JSON format, adding short notes about how to match it and how it was fixed. And finally, we submit pull requests to some designated repository. There were a violate validation check ensures a schema is correct and example still reproduces. So we're gonna implement it without any heavy toolings, just some GitHub actions to validate schema automatically. And later, we even can run small witnesses in such sandbox. And there are three core challenges we are focusing on moving forward. First is our collection. Audit and incident source today are fragmented and spread across the different formats and repositories. Second is a signature generation. It needs to be simple enough for everyone to contribute, but still powerful and accurate. And the third is detection and search. Here we have a balanced presence. But we have to balance between the privacy, speed, and reproducibility, so the results can be shared and verified without exposing sensitive code. So let's go in details for the challenges. There are challenges stays in the vulnerability collection. Audit and incident reports come from many different pieces, contests, professional services, blogs, even open source pull requests. The problem is that they are all used in consistent formats, so it's hard to unify and cross-reference them. So we might mitigate with LLM-based extractions, but yeah, it still remains whether we can trust it or not. And second is patch localization. Patch can also be messy. Sometimes they don't map into the single commit or something they are described in text, but never actually committed into code. And another open question remains: how much original patch code should we actually keep in the somewhat granularity, and should we actually keep in the registry for the reproducibility, function levels and control level, or whole product levels? And another challenge is signature generations. Which signature? The major question is which signature types is actually work. I want to clearly answer. I hope to clearly answer in this session, but we are under testing. I hope we can share it soon. And the main dial is also in abstraction level. When it comes to too concrete, it's too fragile across the compilers or some little modifications. When it comes to too abstract, there are a bunch of false positives. So we're gonna start with the diff anchors and short graphless, and the approaches we mentioned beforehand. And lastly is related to the community issues. We want to users, community members, or users or developers making some signature easily. So then they might need some interface. Anyone can propose and write reviews, fix signatures quickly, and validate it whether it is actually work or not. And the last challenge area is detection and search. And there are three things we care about here. First is privacy. In current settings, we should share every vulnerability-related code and patched code, but some adapters simply cannot share their source code or even signatures themselves. So to address that, we are exploring privacy-preserving matching using techniques like PSI, which is a private set intersections, which lets two parties check for the overlaps without revealing the actual text. And well, maybe in the future, the parts of this could be also implemented in general knowledge proofs or something. And second is speed and scale. We can use regular expression and selector indexes as a lightweight preprocessor over large on-chain data set, and then send only the candidates to different verification. And last thing is the reproducibility. Every detection should include witness result and metadata, so anyone can replay the finding later that way, and the results remain transparent and auditable. Yeah, and there are some plans. Most of things are actually conceptual, and we are planning to open every codes and repository and findings soon, and we're gonna share plans and goals anyway. This year we will test 3 or more the 3 that we mentioned already, and more signature generation methods, and run large-scale on-chain experiments using public datasets like Google BigQuery on next. And if the results are promising, we will refine the schema for the traceability and publish VEX converters and run privacy preserving matching experiments. I hope everything gonna be conducted softly, and we was actually planned to propose to our project through the LFDT labs, but due to the work pressure, I didn't get it. But we are planning to propose to the Linux Foundation decentralized trust labs, and we expect by proposing our project to the LFDT labs, bootstrap the governance and collect some initial cases and validate what works in practices. So to wrap up, let's wrap the whole presentation on. Let's look at where the problems are and what we are proposing to solve them. First, audit reports are full of valuable information, but actually they are underused. And LLM-based analyzers are powerful, but still lack of guarantees and clear explanations for why something is vulnerable. Our proposed approach is the audit-driven signature tracing. The idea is to go from audit report to a bytecode-level signatures for the large-scale on-chain detection, especially for the one-day vulnerabilities. And LLM summarizes the witness data to reduce false positive and improve explainability for LLM-based approaches. And we output everything in VEX competitive format, so these results can plug directly most of CI pipelines, alerting systems, or security policies. So we hope we can open every code and representations this year soon. Yeah, that concludes my talk. Thank you for listening. The bytecode is for the static analyzers, and when it comes to LLMs, we actually give up exact signatures. We give some witnesses and some provenance, some abstracted test code to the LLMs, to hoping they might understand way much better, because they don't even giving such guarantees or test cases for their own findings. There's another question or something? No? Okay, then I will end my session by this. Thank you for listening.